the light you are seeing right now. If you looked at a certain faint smudge in the constellation Virgo, left its source over 1 billion years ago. When it began its journey, multicellular life on Earth was still a relatively recent development. Complex animals had not yet evolved. There were no fish, no forests, no vertebrates of any kind. The light traveled for 1 billion years through the expanding void of space, crossed billions of trillions of kilometers without encountering a single solid object, and arrived at our telescopes, carrying information about one of the most extreme single objects in the entire observable universe. That object is a galaxy called IC 1101, and what it tells us about the scale of the cosmos is more unsettling than almost anything else astronomy has discovered. But to understand why IC 1101 matters, you need to understand what a galaxy actually is, not the word, because the word has become so familiar that most people have lost contact with what it represents. A galaxy is a gravitationally bound system of stars, gas, dust, and dark matter, all moving together through space, all influencing each other through gravity across billions of years of cosmic time. These systems come in different forms: spirals with rotating arms of gas and young stars, ellipticals shaped like three-dimensional blobs of ancient stars, lenticulars sitting somewhere between the two, irregular systems that defy clean classification, but all of them share the same fundamental character. They are islands of matter in a universe that is overwhelmingly empty. Start with the one you already live inside. The Milky Way is a barred spiral containing somewhere between 200 billion and 400 billion stars, including our own sun. It spans roughly 100,000 to 200,000 light-years, from edge to edge, depending on how you define the outer boundary. A light-year is the distance light travels in a single year, moving at 186,000 miles per second. In 12 months of continuous travel at that speed, a single photon covers roughly 6 trillion miles. The Milky Way stretches across approximately 600 quadrillion miles. If you fired a beam of light from one edge of our galaxy toward the opposite edge, that beam would not arrive for 100,000 years. When it left, human beings had not yet invented agriculture. By the time it arrived, our species might be unrecognizable. That is the width of a single average-sized galaxy, even filled with hundreds of billions of stars. The Milky Way is overwhelmingly empty space. The average distance between neighboring stars in our part of the galaxy is roughly 4 light-years, comparable to the distance between our Sun and Proxima Centauri, the nearest known stellar neighbor. If you shrank the Sun to the size of a tennis ball, the nearest star at the same scale would be another tennis ball sitting roughly 1,200 miles away. Everything between them would be vacuum so complete that a spacecraft traveling through it would encounter functionally 0 atoms per cubic centimeter for most of the journey. The galaxy is not a dense swarm. It is a scattering of tiny luminous points, separated by abysses of nothingness so wide that even light requires years to cross them. This emptiness has real consequences. Any civilization on a planet orbiting one of those scattered stars is profoundly isolated from every other star in the galaxy. A radio signal sent from Earth to even a nearby stellar system would take decades to arrive. A spacecraft moving at any speed humanity has ever achieved would require tens of thousands of years to make the same crossing. The distances enforced by galactic structure are so extreme that they may be the primary reason we have never detected a signal from another civilization. The silence of the cosmos is not mysterious when you absorb the scale involved. It is the expected consequence of a galaxy built mostly from nothing. The Milky Way is not special. Among the estimated 2 trillion or so galaxies in the observable universe, Ours is larger than the vast majority, but unremarkable among those of similar type. Most galaxies are dwarfs, tiny systems containing only a few billion stars. Our galaxy is a reasonably massive barred spiral with a moderately active history and a central black hole weighing roughly 4 million times the mass of our Sun. It sits in one of the outer arms of its own structure, orbiting the galactic center at roughly 500,000 miles per hour, completing one full orbit roughly every 225 million years. On the scale of the cosmos, it is a perfectly ordinary place. Look toward the constellation Andromeda on a clear autumn night and you can find a faint smudge of light with the naked eye. That smudge is the Andromeda Galaxy, our nearest major galactic neighbor, sitting approximately 2.5 million light-years from Earth. The light you see tonight left Andromeda before modern humans existed. You are seeing that galaxy as it appeared when our ancestors were still learning to chip stone into tools. And what you are seeing is a galaxy significantly larger than our own. Andromeda spans roughly 220,000 light-years in diameter, more than double the conservative estimate for the Milky Way. It contains approximately 1 trillion stars, at least 2.5 times the number in our galaxy. Its central black hole weighs in at roughly 100 million solar masses, 25 times more massive than ours. Andromeda is the dominant galaxy in our local group, the gravitational family of more than 80 galaxies that includes both the Milky Way and Andromeda as its two largest members. The two galaxies are falling toward each other at roughly 250,000 miles per hour. In approximately 4 to 5 billion years, they will collide, merge, and form a single massive elliptical galaxy that astronomers have already nicknamed Milkdromeda. During that merger, the spiral arms of both galaxies will be destroyed. Stars will be flung into new orbits. The overall structure will transform from two elegant spirals into a single diffuse collection of stars, moving in chaotic paths around a shared center of mass. The merger will not destroy individual stars, because the distances between them are so vast that direct stellar collisions are extraordinarily unlikely. But the galaxies, as recognizable structures, will cease to exist. What remains will be a large elliptical galaxy, billions of old stars orbiting a merged supermassive black hole, with none of the organized structure that currently defines either galaxy. Pause here and feel what has already been described. The Milky Way spans 100,000 to 200,000 light-years and contains hundreds of billions of stars. Andromeda spans 220,000 light-years and contains 1 trillion stars. These are the two largest galaxies in our immediate cosmic neighborhood. And even Andromeda, dominant as it is within our local group, is not remotely close to the upper limit of how large a galaxy can become. To understand that upper limit, you need to understand what a galaxy cluster is and what happens at its center over billions of years of cosmic time. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of individual galaxies, all held together by the combined gravitational pull of visible matter, hot intergalactic gas, and enormous quantities of dark matter. The Virgo cluster, the nearest major cluster to our local group, contains over 1,300 galaxies and lies roughly 54 million light-years away. Larger clusters like the Coma cluster contain thousands of galaxies and span tens of millions of light-years. At the center of nearly every large galaxy cluster sits a special type of galaxy. Astronomers call these brightest cluster galaxies. They occupy the gravitational bottom of the cluster's potential well, the point toward which everything else in the cluster is slowly falling. Over billions of years, smaller galaxies spiral inward through a process called dynamical friction, losing orbital energy and sinking toward the cluster center. When they arrive, the central galaxy absorbs them. It strips their stars, swallows their gas, and incorporates their mass into its own growing body. This process has been repeating since the galaxy cluster first assembled, and in the oldest and most massive clusters, the central galaxy has been feeding for the better part of cosmic history. The result is a type of galaxy classified as a CD galaxy. The lowercase c denotes supergiant. The uppercase D refers to a diffuse stellar envelope, an enormous halo of stars extending far beyond the galaxy's visible core. These halos do not have sharp edges. They fade gradually into the surrounding space, blending almost imperceptibly into what astronomers call intracluster light, the faint glow of stars that have been gravitationally liberated from their parent galaxies and now drift freely through the cluster's shared gravitational field. Where the galaxy ends and the cluster begins is not always a clean distinction. The CD galaxy has eaten so many neighbors and spread its stars so far that its boundaries become genuinely ambiguous. What distinguishes CD galaxies from ordinary elliptical galaxies is not merely size, but structure. A normal giant elliptical follows a brightness profile that decreases smoothly from the center outward according to well-understood mathematical laws. At some radius, the brightness drops below detection thresholds and the galaxy effectively ends. A CD galaxy follows a similar profile in its inner regions, but at a certain distance from the center, the profile flattens. Instead of continuing to fade, the brightness levels off and extends outward in a diffuse envelope that refuses to end neatly. This envelope is the signature of a galaxy built through mergers. Each consumed galaxy adds stars to the outskirts, building up a halo that grows more extended with every absorbed neighbor. The envelope is the archaeological record of billions of years of galactic cannibalism, written in starlight. The supermassive black holes at the centers of CD galaxies are among the most massive ever discovered. While the Milky Way's central black hole weighs roughly 4 million solar masses and Andromeda's weighs roughly 100 million, the black holes in CD galaxies can weigh tens of billions of solar masses. These are objects whose event horizons are wider than our entire solar system. Gravitational engines so powerful that they shaped the thermal properties of gas across millions of light years of cluster space. Among all the CD galaxies ever observed, one has consistently stood out as the most extreme example of visible galactic size. It was first recorded by William Herschel on the 19th of June, 1790. When he pointed his telescope toward a patch of sky near the border of the constellations Virgo and Serpens, and catalogued a faint smudge of light. Herschel had no way of understanding what he was looking at. The concept of galaxies as vast external systems of stars separate from our own Milky Way would not be established for another 130 years. To Herschel, the object was simply another nebula. Another fuzzy patch among hundreds of fuzzy patches scattered across the sky. He noted its position, its approximate brightness, and moved on. The smudge disappeared into the records and waited. It waited through the 19th century, through the development of spectroscopy and the first measurements of stellar distances. It waited through the great debate of the 1920s, when Edwin Hubble proved that certain nebulae were in fact entire galaxies lying millions of light-years beyond the Milky Way. It waited through the construction of ever larger telescopes, through the space age, through the launch of orbiting observatories that could see the universe without atmospheric distortion. And when astronomers finally turned the full power of modern instrumentation toward that faint smudge, recorded by Herschel more than 2 centuries earlier, what they found was one of the most extreme single objects in the observable universe. The galaxy carries the designation IC 1101. It is the 1101st entry in the index catalogue of nebulae and clusters of stars, a supplement to the new general catalogue first published in 1895 by the Danish astronomer Johann Ludwig Emil Dreyer. The name is unglamorous, a filing label rather than a title, but the object it refers to is anything but ordinary. IC 1101 is a supergiant CD galaxy sitting at the exact gravitational center of a massive galaxy cluster called Abell 2029. It lies approximately 1.15 billion light-years from Earth, which means the light we observe from it today left the galaxy when multicellular life on Earth was still a relatively recent evolutionary development. Everything we know about IC 1101 describes the galaxy as it existed over 1 billion years ago. What it looks like now, in this moment, we will never know. By the time the light from this galaxy, as it currently exists, reaches Earth, our planet will have been absorbed by the expanding sun, and the solar system will be unrecognizable. Measuring the size of this galaxy requires some care because galaxies do not have hard edges. They fade gradually from bright cores to dim outer regions to halos of diffuse light that eventually blend into the darkness of intergalactic space. For IC 1101, the most commonly used measurements give an isophotral diameter, measured at a specific surface brightness threshold, of approximately 400,000 to 550,000 light. The lower estimate comes from measurements taken in visible blue light using the standard method recommended for galaxy catalogs. The higher estimate comes from infrared observations by the 2-micron all-sky survey, which detects older, redder stars that glow more prominently at longer wavelengths. Both numbers are already extraordinary. At 400,000 light-years, IC 1101 is roughly 4 times the diameter of the Milky Way. At 550,000 light-years, it approaches 6 times the diameter, but these measurements only describe the galaxy's brighter stellar body. Beyond that body lies something even more remarkable. Deep imaging observations revealed a vast, diffuse stellar halo extending outward from the core to a radius of approximately 2 million light-years. That gives a total halo diameter of roughly 4 million light-years. Some sources have cited a diameter as large as 6 million light, but this figure likely includes intracluster light, the faint glow of stars that have been stripped from their parent galaxies and now drift freely through the cluster. Gravitationally associated with IC 1101, but arguably belonging to the cluster as a whole rather than to the galaxy itself. Let me try to make the scale tangible, because abstract numbers accomplish nothing if you cannot feel them. The Milky Way at its widest spans about 200,000 light-years. Andromeda spans roughly 220,000 light-years. The distance between the Milky Way and Andromeda is approximately 2.5 million light. Now picture the visible stellar body of IC 1101 placed at the center of our local group of galaxies. At 200,000 to 550,000 light-years across, just the visible body, not the halo, would extend well beyond the Milky Way in every direction. Its bright inner region alone would engulf our galaxy entirely. You would not find the Milky Way at the edge of IC 1101. You would find it embedded inside, swallowed, a minor structure within a vastly larger one. Now extend the picture to include the halo. At a radius of 2 million light-years, the diffuse stellar envelope of IC 1101 reaches nearly to the distance of Andromeda itself. The halo of a single galaxy would span a significant fraction of the gap between the 2 largest galaxies in our local group. If IC 1101 were placed at the Milky Way's location, it would not merely dwarf our galaxy. It would engulf Andromeda, the large Magellanic Cloud, the small Magellanic Cloud, the Triangulum Galaxy, and nearly every other galaxy in the local group. a single galaxy occupying the space that our entire galactic neighborhood currently fills. Imagine you could travel at the speed of light, the absolute fastest anything can move in our universe. Starting at one edge of IC 1101's stellar body and flying toward the other, you would travel for more than 400,000 years before emerging on the far side. If you began that journey when Neanderthals still walked the Earth alongside early modern humans, you would not have arrived yet, and that only crosses the stellar body. To traverse the full halo from one edge to the other, your journey at light speed would take roughly 4 million years. When you began, the genus Homo had barely appeared on the African savanna. By the time you finished, you would have traveled for the entire span of human evolutionary history and then continued for millions of years beyond it. IC 1101 contains approximately 100 trillion stars. That is a ratio of roughly 250 to 500 times more stars than the Milky Way, and about 100 times more than Andromeda's 1 trillion. These are stars that formed billions of years ago in the dozens, perhaps hundreds, of smaller galaxies that IC 1101 consumed over its long history. Each wave of mergers brought in new stellar populations, which were gravitationally mixed and redistributed throughout the growing body of the central giant. The result is a galaxy whose starlight is not homegrown but inherited, assembled from the contributions of countless smaller galaxies that no longer exist as independent objects. IC 1101 is not a spiral galaxy. It does not have the organized, rotating disk of stars and gas that characterizes galaxies like the Milky Way and Andromeda. It is a massive, roughly spheroidal collection of old stars that have been gravitationally scrambled by billions of years of mergers. Whatever spiral structures its progenitor galaxies once possessed were destroyed long ago, torn apart and absorbed into the chaotic orbits of the final merged product. To understand the violence of that construction process, think about what a single galactic merger actually looks like. When two large galaxies collide, the event unfolds over hundreds of millions of years. First, the dark matter halos, invisible but gravitationally dominant, begin to interpenetrate. Then tidal forces stretch both galaxies into distorted shapes, pulling streams of stars into long tails that can extend millions of light years into intergalactic space. Gas clouds in both galaxies compress, triggering violent bursts of star formation. The supermassive black holes at the centers of both galaxies spiral inward toward each other, dragged by dynamical friction, eventually merging in an event that releases gravitational waves detectable across the universe. The entire process is chaotic, destructive, and creative simultaneously, forging a new and larger galaxy from the wreckage of two smaller ones. Now imagine that process happening not once, not twice, but dozens of times over the course of 10 billion years. Each merger adds mass. Each merger destroys existing structure and replaces it with a larger, more diffuse configuration. Each merger brings in new stars, new gas, new dark matter, and sometimes a new supermassive black hole that must be absorbed by the existing central engine. IC 1101 is the end product of that violence. The scar tissue of a billion years of cosmic collisions, smoothed over time into the golden, featureless ball of ancient starlight that telescopes reveal today. At the center of IC 1101 lies a supermassive black hole whose estimated mass ranks among the highest ever measured. Different methods produce different estimates, but the range spans from roughly 40 billion to 100 billion solar masses. To appreciate what these numbers mean, compare them to the supermassive black hole at the center of the Milky Way, Sagittarius A star, which weighs roughly 4 million solar masses. The black hole in IC 1101 outweighs ours by a factor of 10,000 to 25,000. It is not merely larger, it belongs to a completely different category of gravitational object. A 2017 study using Hubble Space Telescope imaging found that IC 1101 possesses the largest known galactic core of any galaxy observed to date. The core radius measures approximately 14,000 light-years, roughly an order of magnitude larger than the cores of other well-studied giant elliptical galaxies. This oversized core is believed to be the result of a process called core scouring, in which merging supermassive black holes during past galactic collisions gravitationally ejected stars from the central region, carving out a vast depleted zone. The physics of core scouring is both elegant and violent. When two galaxies merge and their central black holes spiral toward each other, the pair forms a gravitationally bound binary system in the merged galaxy's core. As the binary tightens, it interacts with nearby stars through a gravitational mechanism called three-body scattering. Stars that wander close to the binary are flung outward at high velocity, expelled from the core like projectiles from a slingshot. Each ejection removes mass from the central region and transfers energy to the remaining stars, causing them to spread outward. Over millions of years, this process excavates a cavity in the galaxy's center, creating the diffuse, depleted core that observations reveal. The more mergers a galaxy has experienced, the more black hole binaries have formed and scoured the core, and the larger the resulting cavity becomes. For IC 1101, the mass deficit in the core, the amount of stellar mass that has been ejected by the process, has been estimated at roughly 490 billion solar masses. Consider what that means. 490 billion solar masses is larger than the total stellar mass of most galaxies in the observable universe. The Milky Way's total stellar mass is estimated at roughly 50 to 60 billion solar masses. IC 1101's core deficit alone exceeds the entire stellar content of our galaxy by a factor of 8 to 10. The galaxy has thrown away more stars from its center than the Milky Way contains in total. These ejected stars did not vanish. They were scattered into the outer halo and into the surrounding cluster, contributing to the diffuse envelope of light that extends millions of light-years from the core. The halo of IC 1101 is partly built from the debris of its own internal violence, stars exiled from the center by the gravitational tantrums of merging black holes. IC 1101 is not forming new stars in any significant quantity. The mergers that built it also heated and expelled the gas needed for star formation. There are no glowing nebulae, no stellar nurseries, no blue supergiant stars blazing with the light of recent creation. IC 1101 glows with the steady, fading light of ancient stars, a cosmic monument to a violent past that has now grown quiet. The galaxy's environment reinforces its dominance. Abell 2029 is one of the densest galaxy clusters in the sky, containing thousands of galaxies, including hundreds of giant ones. Yet IC 1101 alone accounts for roughly a quarter of the entire cluster's visible light output, a single galaxy producing 1/4 of the luminosity of a structure containing thousands of galaxies. The cluster itself is enveloped in an enormous cloud of superheated gas that glows in X-ray wavelengths, reaching temperatures of roughly 100 million degrees Celsius. This gas is held in place by the combined gravitational pull of the cluster's dark matter, and IC 1101 sits at the very center of this hot gas cloud, at the deepest point of the cluster's gravitational potential well. The history of how IC 1101 reached this size is written in the properties of its halo. The smoothness of the stellar envelope suggests that most of the major mergers occurred early in the cluster's history, when the universe was younger and galaxy interactions were more frequent. Studies of brightest cluster galaxies in general suggest that these objects assembled roughly half of their mass through mergers that occurred more than 8 billion years ago, with subsequent growth proceeding more slowly as the rate of galactic infall decreased. IC 1101 likely consumed dozens of major galaxies and hundreds of smaller ones over its lifetime. Each collision added to its mass, expanded its halo, and fed its central black hole. Every major galaxy that fell into the center of Abell 2029 over the past 10 billion years was absorbed into IC 1101. Galaxies that may have been comparable in size to the Milky Way, galaxies that may have contained their own planetary systems, their own complex chemistry, perhaps even their own biological evolution, all of them consumed, all of their stars now orbiting within the body of a single, vast, slowly fading giant. The galaxy is not just large, it is a graveyard. A monument built from the remains of everything that wandered too close to the center of the cluster over cosmic time. This connects to something uncomfortably close to home. The Milky Way and Andromeda are falling toward each other and will merge in roughly 4 to 5 billion years. That merger will destroy both spiral galaxies and create Milkdromeda, a single massive elliptical galaxy containing the combined stellar populations of both. Milkdromeda will be large by current standards, perhaps over 1 trillion stars, a respectable elliptical galaxy with a substantial dark matter halo and a merged supermassive black hole. It will be the dominant galaxy in whatever remains of the local group, but IC 1101 reveals that Milkdromeda would not be the end of anything. It would be the beginning, because IC 1101 was built from exactly this kind of merger, repeated over and over across billions of years. If the Milky Way and Andromeda happened to sit at the center of a massive galaxy cluster instead of in the relatively sparse local group, their merger product would not be a final form. It would be an appetizer, a single course in a meal that lasts for 10 billion years and ends with something the size of IC 1101. Milkdromeda, the galaxy that would one day contain every star and planet we have ever known, would add barely 1% to the giant's total mass. Its 1 trillion stars would be absorbed, scattered, and forgotten in the vast golden halo within a few 100 million years. Nothing about Milkdromeda, not its structure, not its history, not any civilizations that might still exist within it, would survive as a recognizable feature. The product of the Milky Way's and Andromeda's cosmic collision would vanish into the body of the larger galaxy like a raindrop falling into a lake. For a long time, the story seemed settled. The biggest visible galaxy was IC 1101. The record measurement was 4 to 6 million light-years, depending on how you measured the halo, and the emotional conclusion was clear: a galaxy bigger than our entire local group. But the story did not end there, because the universe was not finished revealing what it had built. When astronomers first began detecting radio wavelength signals from the sky in the mid-20th century, they discovered something unexpected. Certain galaxies appear to have enormous structures extending far beyond their visible stellar bodies. These were not made of stars. They were vast reservoirs of magnetized plasma, inflated by relativistic jets of material fired from the vicinity of the galaxy's central supermassive black hole. Heated to extreme energies, the electrons in these structures emitted synchrotron radiation detectable by radio telescopes. These radio lobes glow only in radio wavelengths, invisible to any optical telescope ever built. The mechanism Producing these jets is one of the most violent and physically extreme processes in the entire cosmos. At the center of certain galaxies, the supermassive black hole is actively accreting material, pulling in gas and dust from its surroundings and forming a rapidly spinning accretion disk. This disk is a superheated maelstrom of plasma spiraling inward at velocities approaching the speed of light, compressed by gravitational forces so intense that the inner regions reach temperatures of hundreds of millions of degrees, a fraction of the infalling material. Channeled by powerful magnetic fields threading the accretion disk and the spinning black hole's ergosphere, gets launched outward along the black hole's rotational axis in two tightly collimated beams, called relativistic jets. These jets travel at velocities approaching the speed of light, sometimes exceeding 99% of it. They carry the power output of trillions of suns in two narrow beams that punch through the galaxy's interstellar medium and continue outward into intergalactic space. As the jets interact with the surrounding gas, they slow down, spread out, and inflate enormous lobes of magnetized plasma. These lobes grow over millions of years, fed continuously by the jets, expanding outward until the pressure of the intergalactic medium balances the energy being pumped into them. Most radio galaxies produce lobes that extend a few 100,000 light-years from the central galaxy, comparable in scale to the galaxy's own stellar body. But there is a subclass called giant radio galaxies whose radio lobes extend to truly extraordinary distances, reaching lengths measured not in hundreds of thousands of light-years, but in millions. These are structures so vast that they do not merely extend beyond their host galaxy. They extend beyond the galaxy's local environment, beyond the scale of galaxy groups, into the spaces between cosmic web filaments. In February of 2022, a team of astronomers led by Martesian OE at the Leiden Observatory in the Netherlands published a paper announcing the discovery of a giant radio galaxy they named Alcyone, after one of the giants of Greek mythology. The galaxy was identified in data from the Low Frequency Array, or LOFAR, a network of roughly 20,000 individual radio antennas distributed across 52 stations in Europe. LOFAR operates at frequencies far below what optical telescopes detect, and its sensitivity to faint diffuse radio emission makes it ideally suited for detecting the extended lobes of giant radio galaxies. What OE and his colleagues found was remarkable. Alcyone possessed a radio structure spanning approximately 5 megaparsecs in projected length, which translates to roughly 16 million light-years from one lobe edge to the other. To put that in context, the Milky Way is approximately 100,000 to 200,000 light-years across. Alcyone's radio structure was roughly 100 times the diameter of the Milky Way. Laid end to end, you would need 100 Milky Way galaxies to match the span of this single radio structure. The media response was immediate and in many cases misleading. Headlines declared Alcyone the largest galaxy in the universe, but this framing obscured a critical distinction. Alcyone's host galaxy, the actual stellar body at the center of the radio structure, is not exceptional. Its stellar mass is estimated at roughly 240 billion solar masses, only a few times that of the Milky Way and far smaller than IC. 1,101's estimated 100 trillion stars. Its central supermassive black hole weighs approximately 390 million solar masses, roughly 100 to 250 times less massive than the black hole in IC 1101. By every measure of the visible stellar body, the host galaxy of Alcyone is unremarkable. What makes it extraordinary is not its galaxy, it is its jets. The most plausible explanation for Alcyone's enormous radio structure is that its growth was determined not by the power of the central engine, but by the density of the surrounding environment. Alcyonius resides in a filament of the cosmic web where the intergalactic medium may be less dense than average, with less resistance pushing back against the expanding lobes. The same modest jet power that would produce ordinary-sized lobes in a denser environment instead produced a structure spanning 16 million light-years in the relative vacuum of a sparse cosmic filament. The engine is modest. The output is colossal. Radio lobes are not typically considered part of a galaxy's size in standard astronomical usage. They are ejected material expelled from the galaxy rather than material contained within it. The distinction reflects a genuine scientific question about what a galaxy actually is. Is a galaxy defined by its stars, by the gravitational extent of its dark matter halo, by the furthest reach of any structure physically connected to its central engine? The answer determines whether Alcyonius is the largest galaxy ever found, or merely the galaxy with the largest radio ejector ever found. And those are meaningfully different claims. But even as astronomers were processing the implications of Alcyonius, the record was already being broken again. In September of 2024, a paper published in the journal Nature by a team, again led by Martesian OE, announced the discovery of an even larger giant radio galaxy. This one was named Porphyrion, after another giant of Greek mythology, and its scale made Alcyonius look modest by comparison. Porphyrion's radio jets span approximately 7 megaparsecs, or roughly 23 million light-years from end to end. That is 140 times the diameter of the Milky Way. The host galaxy of Porphyrion lies 7.5 billion light-years from Earth, meaning the jets existed when the universe was only 6.3 billion years old, less than half its current age, despite its extreme youth in cosmic terms. The central black hole generated jets with a combined power output equivalent to the energy of trillions of suns, punching plasma into intergalactic space at nearly the speed of light, and inflating lobes that stretched across a volume of space, comparable in scale to the gaps between filaments of the cosmic web. Porphyrion's discovery carried implications that went far beyond the question of galactic size records. The research team calculated that the jets span roughly 2/3 the radius of a typical cosmic void at that epoch of universal history. This means a single galaxy's outflows were reaching scales that interact not just with the galaxy's local environment, but with the large-scale structure of the universe itself. The jets were threading through the cosmic web, potentially magnetizing the intergalactic medium, heating the gas between filaments, and influencing the formation and evolution of other galaxies located millions of light-years from the source. OE and his colleagues noted that their findings suggest supermassive black holes do not only hold sway over the galaxy, but also over the cosmic web that surrounds them. This is not a minor addendum to our understanding of galactic physics. It is a fundamental Galaxies are not just objects within the cosmic web. Some of them are architects of the cosmic web, shaping its properties across scales that rival the web's own. Organizational structure and even Porphyrion's record did not last. By late 2024, another radio galaxy designated TXS 0033+252 was identified with an estimated radio structure spanning approximately 26 million light. The records are falling faster than the scientific community can fully absorb them, driven by the unprecedented sensitivity of LOFA and the growing recognition that giant radio galaxies are far more common than previously believed. A citizen science effort associated with the LOFR surveys has already identified more than 10,000 jet pairs spanning roughly 3 million light-years or more. These are not rare curiosities. They are a population a class of objects that the universe produces routinely. Now lay these measurements out in sequence and feel the ladder they form. The Milky Way, 100,000 to 200,000 light-years. Andromeda, 220,000 light. IC 1101's stellar body, 400,000 to 550,000 light. IC 1101's full halo, approximately 4 million light-years. Alcyonius's full radio structure, approximately 16 million light. Porphyrion's full radio structure, approximately 23 million light-years. TX S0033 plus 252, approximately 26 million light-years. Each step on that ladder does not merely increase the number, it changes the category. The jump from the Milky Way to Andromeda is a jump within the same class of objects. Spiral galaxies of roughly similar structure. The jump from Andromeda to IC 1101 is a jump from a large spiral to a supergiant elliptical. A fundamentally different type of galaxy built through fundamentally different processes. The jump from IC 1101's stellar body to its halo is a jump from the galaxy's bright interior to its fading gravitational periphery. And the jump from IC 1101's halo to the radio structures of Alcyonius and Porphyrion is a jump from assembled starlight to relativistic plasma, from gravitational architecture to energetic outflow, from the galaxy as a collection of stars to the galaxy as a source of influence that extends across cosmological distances. At each step, the previous reference point shrinks. The Milky Way, which felt impossibly vast at the start, becomes a rounding error by the time you reach IC 1101. IC 1101, which seemed like the ultimate expression of galactic scale, becomes a dot at the center of Porphyrion's radio structure. Consider what this means for the way we understand our own place in the cosmos. Every measurement humanity has ever made of the universe has been made from inside the Milky Way. Every telescope, every space probe, every photon we have ever collected has arrived at instruments located within our galaxy. Our entire understanding of the cosmos is built on observations made from a platform that at the scales being considered barely qualifies as a location. We are not observing the cosmos from a meaningful vantage point. We are observing it from a pixel, a single unremarkable pixel in a structure, so vast that the structure itself is unremarkable compared to what the universe can build. Every astronomy textbook, every map of the cosmic web, every diagram of the observable universe places the Milky Way at the center because that is where the observer happens to stand. But the centrality is observational, not physical. There is nothing special about our position. An observer in IC 1101 would see a different observable universe centered on a different point, containing different galaxies at different distances. An observer in Porphyrion's host galaxy would see yet another. Every location in the cosmos is the center of its own observational sphere, and none of them is privileged. When you compare Porphyrion's scale directly to the Milky Way, the numbers produce something that stops feeling like astronomy and starts feeling like philosophy. Porphyrion spans 23 million light-years. The Milky Way spans 200,000. The ratio is roughly 115 to 1. If Porphyrion's radio structure was scaled to the length of a football field, the Milky Way would span barely a single yard of the total distance. Our entire galaxy, with all its stars, all its planets, all its civilizations that might exist, reduced to a single stride on a playing surface. A galaxy containing 400 billion stars, a supermassive black hole, spiral arms spanning 100,000 light-years, and it would register as nothing, a fluctuation below the noise floor. Not marginalized, not diminished, erased. This is not a poetic exaggeration. It is a direct consequence of the numbers. What is the largest galaxy we have ever found? The answer depends entirely on what you choose to measure. If you define a galaxy by its visible stellar body, IC 1101 remains one of the strongest candidates. With an isophotal diameter of 400,000 to 550,000 light-years and a diffuse stellar halo extending to roughly 4 million light-years. By every metric used to evaluate visible galactic size, it sits at or near the top of the distribution. But if you define a galaxy by the total extent of any coherent physical structure connected to its central engine, including radiolobes inflated by relativistic jets, then the record belongs to objects like Porphyrion and its successors, whose physical extents of 23 to 26 million light-years exceed the halo of IC 1101 by factors of roughly 6 to 7. The tension between these two definitions is not a flaw in astronomy. It reflects a genuine physical reality. Galaxies are not simple objects. They are multi-layered systems with stellar bodies, dark matter halos, gas reservoirs, magnetic fields, and in some cases, relativistic outflows that extend far beyond anything the stars alone could reach. An astronomer studying stellar populations might define galaxy size by the extent of the stars and conclude that IC 1101 is the largest. A radio astronomer studying jet physics might define galaxy size by the extent of the radio structure and conclude that Porphyrion holds the record. Both are correct within their frameworks. The universe simply does not provide a single unambiguous answer. But here is what matters more than the record itself. The existence of these giant radio structures tells us something deeply uncomfortable about the range of scales the universe can produce from a single galactic source. When Alcyonius was discovered, astronomers were surprised not by the existence of giant radio galaxies, which had been known for decades, but by the fact that the host galaxy was so ordinary. Nothing about the central engine was exceptional, yet it produced a radio structure spanning 16 million light-years. The implication was that giant radio galaxy growth might not require unusual central engines. It might require only the right environment, a low-density region of the cosmic web where the intergalactic medium offers minimal resistance to the expanding lobes, allowing them to grow to extraordinary sizes without being confined by external pressure. Porphyrion complicated this picture further, because its host galaxy is more massive, roughly 10 times the mass of the Milky Way, and its black hole operates in a different mode, a radiative mode rather than the jet mode typical of most giant radio galaxies. This was unexpected, because radiative mode black holes were not previously known to produce jets of this scale. The discovery implied that the conditions for giant jet growth might be more varied and more common than astronomers had assumed. LOFA has so far surveyed only about 15% of the northern sky. The population of giant radio galaxies identified already numbers in the thousands, and the survey is nowhere near complete. Researchers studying this field have stated that astronomers may be looking at the tip of the iceberg. The true population of structures spanning millions of light-years could be vastly larger than current catalogues suggest. The records will keep falling. The remaining 85% of the northern sky that LOFA has not yet surveyed almost certainly contains giant radio galaxies that surpass everything in current catalogues, and LOFA itself will eventually be surpassed by the Square Kilometre Array, an international radio telescope project currently under construction across sites in South Africa and Australia. When completed, it will be the most sensitive radio telescope ever built, with a total collecting area of approximately 1 square kilometre and a sensitivity that exceeds LOFA by an order of magnitude. The Square Kilometre Array will survey the entire sky both hemispheres, at frequencies and resolutions that make current instruments look primitive. If giant radio galaxies are as common as Lawfast's partial survey suggests, the square-kilometer array will discover them in the hundreds of thousands. It will map the full population of giant jet structures across the observable universe, revealing for the first time the true statistical distribution of the largest galactic structures in existence. There is no indication that we have found the largest galactic structure the universe has produced. There is no theoretical ceiling that says radio jets cannot extend beyond 30 million light-years, or 40 or 50. The limiting factor appears to be the density of the intergalactic medium, which varies from region to region across the cosmic web. In denser environments, jets are confined and cannot grow as large. In sparser environments, in the voids between filaments where the intergalactic medium is thinnest, jets can expand with minimal resistance. If there exists somewhere in the unobserved universe a super black hole embedded in a galaxy sitting in an unusually sparse region of the cosmic web with just the right accretion rate and just the right jet orientation, its radio structure could potentially extend to scales we have not yet observed. The existence of these structures changes the way we must think about what a galaxy is and what role it plays in the universe. For most of the history of astronomy, galaxies were treated as discrete objects, islands of stars separated by vast empty spaces. The space between galaxies was considered largely inert. Galaxies were the actors. The space between them was the stage. But giant radio galaxies dissolve this distinction. When a single galaxy's jet spans 23 million light-years, threading through the cosmic web, magnetizing the intergalactic medium, heating gas in neighboring filaments, the galaxy is no longer confined to its own island. Its influence has leaked out, contaminated the space between structures, blurred the boundary between actor and stage. A galaxy is supposed to be a bounded object, a collection of stars and gas and dark matter held together by gravity, distinct from its surroundings, definable, measurable. But when a galaxy's radio lobes extend 23 million light-years into intergalactic space, is the structure still a galaxy? When a galaxy's stellar halo merges imperceptibly into the intracluster light of its parent cluster, where does the galaxy end and the cluster begin? When a galaxy's jets magnetize the cosmic web across scales rivaling the distances between filaments, is the galaxy's influence truly local? These are not rhetorical questions. They are active areas of research, and the answers, when they come, will likely reveal that the boundaries we draw around galaxies are human constructs imposed on a cosmos that does not recognize them. To understand how the universe arrived at this state, it helps to go back much further, to the conditions that gave rise to the first galaxies. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma of matter and radiation, opaque to light in the way that the interior of a star is opaque today. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms in an event called recombination, and the universe became transparent for the first time. The radiation released at that moment has been traveling through space ever since, cooling as the universe expanded, and is observed today as the cosmic microwave background radiation, the faint afterglow of the Big Bang. The universe that emerged from recombination was not the universe we see today. It contained no stars, no galaxies, no planets. It was a nearly uniform sea of neutral hydrogen and helium with tiny density variations, seeded by quantum fluctuations in the very early universe. The period that followed, roughly from 300,000 years to about 1 billion years after the Big Bang, is called the Cosmic Dark Ages, because the universe was dark, containing no sources of light. The first stars formed from the collapse of dense regions of primordial gas into objects that were, by modern stellar standards, enormous. These population 3 stars, as astronomers call them, may have been hundreds or even thousands of times more massive than the Sun. They burned intensely, lived briefly, and died in spectacular supernova explosions that seeded the surrounding gas with the first heavy elements produced by nuclear fusion in stellar cores. Ultraviolet radiation from these first stars began to reionize the surrounding neutral hydrogen, gradually making the universe transparent to ultraviolet light in a process called reionization that extended from roughly 200 million years to about 1 billion years after the Big Bang. The first galaxies assembled around the same time as the first stars, small dark matter halos, regions where dark matter had gravitationally collapsed into self-contained structures, provided the gravitational scaffolding around which ordinary matter accumulated. Gas falling into these halos formed stars, and the first galaxies emerged as small, irregular collections of young stars embedded in dark matter. These early galaxies were very different from the large, organized structures we see in the nearby universe today. They were smaller, clumpier, and far more actively star-forming, because they were embedded in gas-rich environments and experiencing frequent mergers with neighboring systems. Over the following billions of years, these small early galaxies merged and grew. Smaller halos fell into larger ones through the hierarchical process of structure formation. The cosmic web of filaments and voids took shape as matter was redistributed by gravity on ever larger scales. Galaxy clusters assembled at the intersections of cosmic web filaments, accumulating the products of billions of small-scale mergers into single, massive systems. And at the centers of the largest clusters, the first CD galaxies began to form through the relentless process of galactic cannibalism. The observable universe spans approximately 93 billion light-years in diameter. That figure might seem paradoxical given that the universe is only about 13.8 billion years old, and since nothing can travel faster than light, you might expect the observable universe to extend no more than 13.8 billion light-years in every direction. But the universe has been expanding since the Big Bang, and distant regions of space have been carried away from us by that expansion faster than light travels. The most distant objects we can observe are ones whose light left when the universe was very young and very small, and those regions have since been carried to their current position by cosmic expansion within the sphere of observable space. Matter is not distributed uniformly. It is organized into a vast network of structures called the cosmic web. The cosmic web consists of 3 primary elements: filaments, walls, and voids. Filaments are long, thread-like concentrations of matter, some spanning hundreds of millions of light-years, along which galaxies and galaxy clusters are preferentially located. Walls are flatter, sheet-like structures where filaments intersect and matter accumulates in 2-dimensional patterns. And voids are the vast, nearly empty regions of space that occupy the majority of cosmic volume. Regions where the density of matter is far below the cosmic average and galaxies are sparse or absent. This structure emerged from the tiny density fluctuations that existed in the very early universe, when quantum mechanical variations in the density of matter were imprinted on the cosmic microwave background radiation. Regions that were slightly denser than average attracted more matter through gravity, becoming denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming emptier over time. Over billions of years, this process amplified the initial fluctuations into the striking filamentary structure we observe today. The cosmic web is the gravitational skeleton of the universe, and every galaxy cluster, Every structure we have been discussing exists embedded within it. Galaxy clusters form at the intersections of cosmic web filaments, where multiple streams of infalling matter converge. The cluster draws galaxies in along the filaments like water flowing down drains, accumulating mass from a vast cosmic catchment area. The brightest clustered galaxy at the center of such a system is therefore not just the most massive member of its local cluster. It is the beneficiary of mass flowing in along multiple cosmic web filaments, fed by a gravitational influence that extends across tens or hundreds of millions of light years. This is why IC 1101 is connected not just to Abell 2029, but to the surrounding large-scale structure. The galaxy's major axis is aligned with the axis along which Abell 2029 accretes material from the neighboring cluster, Abell 2033. This is not coincidental. The galaxy has grown along the same large-scale channels through which matter has been flowing for billions of years. IC 1101 is not merely the product of local galactic mergers. It is the product of large-scale cosmic structure, the accumulated endpoint of matter flowing through a network of filaments across hundreds of millions of light-years of cosmic space. IC 1101 is overwhelmingly red and gold in color, reflecting a stellar population that formed billions of years ago and has been slowly aging ever since. It is a galaxy whose star-forming days are long past. The relationship between star formation and galactic evolution is governed by a complex interplay of forces. Star formation requires cold, dense gas to collapse under gravity. But the processes that make galaxies grow, mergers, black hole activity, the heating of infalling gas by the gravitational potential of the cluster itself, all tend to disrupt or expel the cold gas needed for star formation. In the most massive galaxies, this feedback between growth and the suppression of star formation has operated for so long that the supply of cold gas has been essentially exhausted. The galaxies have consumed or expelled the fuel they would need to build new generations of stars. Black hole feedback is a particularly important mechanism in this process. When a supermassive black hole is actively accreting material at a high rate, the energy released by the accretion disk can drive powerful winds and jets that sweep gas out of the galaxy. These outflows not only remove gas from the immediate vicinity of the black hole, but can also heat the surrounding medium, preventing it from cooling and forming new stars for extended periods. In galaxy clusters, this feedback operates on cluster-wide scales. The jets from the central black hole can heat the hot intracluster gas, suppressing, cooling, and preventing the formation of new stars throughout the cluster core, not just in the central galaxy itself. This is the phenomenon known as AGN feedback, where AGN stands for active galactic nucleus, the bright central region powered by an accreting supermassive black hole. AGN feedback is now recognized as one of the most important processes shaping the evolution of galaxies and galaxy clusters. Without it, the most massive galaxies should be far more massive than they are, because simulations of galaxy formation without AGN feedback consistently produce central galaxies that are too massive and too blue, still forming stars at rates inconsistent with observations. Including a GN feedback in simulations brings galaxy masses and star formation rates into agreement with observations, which is why astrophysicists regard it as a key component of realistic galaxy formation models. The giant radio galaxies, like Alcyonius and Porphyrion, represent an extreme form of AGN feedback in which the energy output of the central black hole is not just modifying the galaxy's own star formation, but reaching across millions of light-years to affect the intergalactic medium and the properties of the cosmic web itself. The origin of magnetic fields in the intergalactic. Medium is a problem that these giant radio galaxies may help resolve. Observations confirm that the gas between galaxies is permeated by weak but measurable magnetic fields. These fields are not generated by any local process within individual galaxies, but appear to be a property of the intergalactic medium itself. Giant radio galaxy jets offer a potentially powerful explanation. If jets spanning tens of millions of light-years routinely inject magnetized plasma into the intergalactic medium, they could be the primary source of cosmic magnetism on the largest scales. Porphyrion's discovery strengthened this hypothesis by demonstrating that jet structures can reach sizes comparable to the cosmic web itself, placing magnetized plasma exactly where it would need to be to explain the observed intergalactic fields. The jets of Porphyrion and structures like it may not merely be curiosities at the extreme end of the galactic size distribution. They may be fundamental contributors to the electromagnetic environment of the universe, responsible for magnetizing the cosmic web and influencing the conditions for galaxy formation across vast volumes of space. Every large galaxy is also embedded in a dark matter halo that extends far beyond the visible stellar body. Dark matter, which does not interact with electromagnetic radiation and is therefore invisible to all telescopes that detect light, makes up roughly 85% of the total matter content of the universe. Its presence is inferred from its gravitational effects on matter and on the paths of light passing through regions where it is concentrated. For the Milky Way, the dark matter halo is estimated to extend to a radius of roughly 300,000 to 600,000 light-years, well beyond the visible disk of stars. For IC 1101, the dark matter halo encompasses the entire visible stellar body and likely extends well beyond the stellar halo, connecting to the larger dark matter structure of Abell 2029. The cluster itself is embedded in an even larger dark matter concentration that extends across tens of millions of light-years and connects along dark matter filaments to neighboring galaxy clusters and groups. If you include dark matter halos in the definition of galaxy size, the sizes become even more extreme. But dark matter halos do not have sharp edges either. Their density profiles decline smoothly with distance from the center, and defining a boundary requires choosing an arbitrary density threshold. Different conventions give different answers, and the outer regions of dark matter halos blend continuously into the background density of the cosmic web. The ambiguity of galaxy boundaries is even more pronounced when dark matter is included. This is why the question of what the largest galaxy is cannot be answered with a single clean number. It depends on what you are measuring, which wavelengths you use, which boundaries you define, and which components of the galaxy you choose to include. The universe does not package galaxies with labels indicating their official size. It produces continuous distributions of matter and energy that humans then carve up into named objects, using whatever definitions seem most useful for the questions being asked. IC 1101 is the most extreme example of visible galactic size by most definitions. Applied to stars and stellar light, giant radio galaxies are the most extreme when the definition is extended to include relativistic outflows. Dark matter halos are the most extreme when they are included. Each definition reveals something real and important about the universe, and none of them is the uniquely correct answer. This lesson, that our categories and definitions are human constructs imposed on a universe that does not share our preference for clean boundaries, is one of the deepest insights that the study of extreme galaxies offers. Galaxies are not natural kinds in the philosophical sense, objects with intrinsic essential properties that make them what they are. They are convenient concentrations of matter and energy that shade gradually into their environments. The word galaxy points to a real feature of the universe, a genuine overdensity of stars and gas and dark matter with a roughly coherent dynamical history. But the precise boundary of that feature is a choice, not a discovery. For all its incomprehensible size, IC 1101 will not last forever. The universe has a future as well as a past, and on cosmological timescales, that future involves processes that will gradually erase the structures we see today. The expansion of the universe is accelerating, driven by dark energy, the mysterious component that makes up roughly 68% of the total energy content of the cosmos. As the expansion accelerates, galaxies that are currently far away will be carried to distances beyond which their light can never reach us, disappearing below our horizon forever. On timescales of tens of billions of years, the stars in IC 1101 will exhaust their nuclear fuel and go dark. The most massive stars burn through their fuel in millions of years and explode as supernova. Stars like our Sun last about 10 billion years. The smallest red dwarf stars may burn for trillions of years, but even the longest-lived stars will eventually exhaust their hydrogen fuel and end their lives. On timescales of 100 trillion years or more, even red dwarfs will have exhausted their fuel, and IC 1101, like every other galaxy in the cosmos, will fade to darkness. The 100 trillion stars of IC 1101 will leave behind stellar remnants, white dwarfs, neutron stars, and black holes, on timescales of 1,000 trillion years or more. Even the orbital motions of these remnants will decay as they lose energy through gravitational wave emission, and matter will gradually fall toward the central supermassive black hole, eventually through a process called proton decay. If the relevant physics is correct, even the atomic nuclei themselves will disintegrate. On the longest timescales accessible to physics, even black holes evaporate through Hawking radiation, leaving nothing but a diffuse cloud of photons and elementary particles. The universe has a destiny as well as a history, and that destiny is the gradual dissolution of all structure into thermal equilibrium, the maximum entropy state sometimes called the heat death of the universe. On that timescale, the distinction between the largest galaxy and the smallest is irrelevant. All structure, all complexity, all organization will have dissolved. The magnificent hierarchy of scales we have been exploring, from the Milky Way to IC 1101 to the giant radio galaxies spanning tens of millions of light-years, is a feature of the universe at a particular moment in its history. The relatively brief period during which stars burn, galaxies exist, and the cosmos is organized enough for creatures like us to look up at the sky and ask questions about what they see. Astronomers sometimes call this the stelliferous era, the age of stars, which began roughly 100 million years after the Big Bang, when the first stars ignited, and will end roughly 100 trillion years from now, when the last red dwarf burns out. We are living in the middle of this era, at a time when the universe is structured, luminous, and accessible to observation. The largest galaxies we have found are products of this era, assembled through processes that required billions of years of cosmic history, and that will not persist for an infinite future. This temporal context does not diminish the significance of what we observe. IC 1101 is extraordinary by any measure appropriate to the universe as it currently exists. Porphyrion's jets are among the most physically consequential phenomena operating in the present cosmos. The square-kilometer array will reveal populations of structures that will transform our understanding of how the universe organizes matter and energy on the largest scales. And every discovery in this field advances our understanding of the processes that shaped the cosmos we inhabit. What makes the study of the largest galaxies scientifically compelling is precisely the fact that they are not just large, they are large in ways that connect to fundamental questions about the nature of gravity, the physics of black holes, the properties of dark matter and dark energy, the origin of cosmic magnetic fields, and the mechanisms that shaped the large-scale structure of the universe. IC 1101 is not just a big galaxy. It is a probe of the processes that operate at the intersection of galaxy-scale physics. Porphyrion's jets are not just a large structure. They are a demonstration that single galactic engines can influence the physical properties of the cosmos on scales approaching those of the cosmic web itself. There is a specific kind of cognitive vertigo that arrives when you follow this ladder all the way up. You can build a mental model of the Milky Way and hold it in your head as a concept with a shape and a size. You can do the same for Andromeda with some effort. You can even do it for IC 1101 if you anchor it to the comparison with the local group. But you cannot hold Porphyry. You cannot visualize 23 million light-years of relativistic plasma extending from a single point source into the void between cosmic web filaments. The image does not fit. The frame of reference you need does not exist in human experience. The structure is real, measured, confirmed, but it exists beyond the threshold of what our evolved cognitive architecture can render as a picture. And that failure of visualization is not a weakness of science communication. It is the point. The universe at these scales is not supposed to make intuitive sense. It was not built for human comprehension. It was built by gravity, by thermodynamics, by the relentless physics of accretion and ejection operating over billions of years without any awareness that a species on a small planet in a minor, spiral arm would one day try to picture what it had done. The structures exist whether or not we can imagine them. The lobes expand whether or not we can feel their size. The galaxies grow whether or not we have words adequate to describe them. The question of what these discoveries mean for how we think about our own significance connects to how science has historically changed our sense of cosmic place. Every major astronomical revolution has involved a demotion of some kind. The Copernican revolution removed Earth from the center of the solar system. The recognition that our sun is an ordinary star removed us from any privileged stellar position. The discovery that the Milky Way is one among billions of galaxies removed us from any privileged galactic position. And the discoveries we have been discussing of galaxies so massive that our own is a speck within their halos, of radio structures so extended that our galaxy would be undetectable within them, represent a continuation of this pattern. But it is worth being precise about what this demotion means and what it does not mean. It does not mean that our existence is insignificant in any evaluative sense. Significance is a concept that applies within human frameworks of value, and those frameworks are not diminished by the fact that the universe is large. A conversation between two people on Earth is not less meaningful because there are 100 trillion stars in IC 1101. A scientific discovery made by researchers using data is not less important because Porphyrion's jets extend 23 million light-years beyond the galaxy that produced them. What the scale of the universe does mean scientifically is that the processes we observe in extreme galaxies are not exotic exceptions to some gentler cosmic norm. They are part of the same continuum of physical processes that shaped our galaxy, our solar system, and our planet. The same gravity that keeps Earth in orbit around the Sun keeps IC 1101 at the center of Able 2029. The same electromagnetic interactions that power our Sun's nuclear fusion power, the synchrotron radiation in Porphyrion's lobes, the same dark matter that provides the gravitational scaffolding of our galaxy's halo provides the scaffolding for galaxy clusters and the cosmic web. The physics is the same. The scales are different, and understanding the most extreme scales, where the effects are most pronounced and most measurable, illuminates the physics that operates everywhere, the history of the universe, from the quantum fluctuations of the inflationary epoch to the cosmic web of today, is a history of structure growing from the homogeneous to the complex, from the uniform to the filamentary, from the small to the large. The largest galaxies we know of represent the endpoint of that growth process in the current epoch of cosmic history. The most extreme concentrations of matter and energy that gravitational and electromagnetic processes operating over 13.8 billion years have been able to produce, and the fact that they are as extreme as they are, that a single galaxy can contain 100 trillion stars, or that a single black hole can produce a radio structure spanning 23 million light-years, tells us something profound about the efficiency of those processes and the richness of the physical universe. We are observers at a fortunate moment, living in an era when instruments are sophisticated enough to detect these extremes. But when the extremes themselves still exist in accessible forms, the largest CD galaxies are still visible, still fed by the slow infall of material from their clusters, still glowing with the light of their accumulated stellar populations. The giant radio galaxies are still active, or recently active, their lobes still bright enough to detect in radio surveys. The cosmic web is still well organized, its filaments and voids clearly defined, its structure accessible to spectroscopic surveys of galaxy positions and velocities in the far future. None of this will be the case. The accelerating expansion of the universe will carry distant galaxy clusters beyond our observable horizon, leaving only the local group and a few nearby systems in a cosmological bubble of increasing isolation. Stars will exhaust their fuel. Galaxies will fade. The cosmic web will become increasingly diffuse as expansion stretches the filaments to lower and lower densities. The universe will grow colder and emptier and simpler as entropy increases and the structures built by gravity and thermodynamics over billions of years are gradually erased by the same physics that created them. We happen to exist in the right moment to observe these structures at their most impressive. The universe will not look like this forever. What scientists still do not know is substantial. The true upper limit of radio jet extent remains undetermined. The physical mechanisms that allow some black holes to produce jets spanning tens of millions of light years, while other seemingly similar black holes produce jets spanning only a few 100,000 remain incompletely understood. The full population of giant radio galaxies across the observable universe has not been mapped. The contribution of giant jet activity to the cosmic magnetic field and to the overall thermal history of the intergalactic medium is still being quantified. The question of why some galaxies become massive ellipticals while others remain spiral disks, and why some central cluster galaxies reach the extraordinary masses seen in IC 1101, while others in seemingly similar cluster environments remain more modest, continues to be investigated. What is coming next is transformative. The Square Kilometre Array will conduct sky surveys that probe the radio universe at sensitivities that make current instruments look primitive, detecting giant structures that are currently invisible. The population of objects like Alcyonius and Porphyrion that LOFA has begun to reveal will expand by orders of magnitude, and with that expansion will come the data needed to answer the questions that current surveys can only gesture toward. The Rubin Observatory, currently completing construction in Chile and expected to begin full science operations in the late 2020s, will map the stellar populations and structural properties of millions of galaxies with a statistical completeness impossible with current instruments. The James Webb Space Telescope is already transforming our understanding of the early universe, revealing the properties of galaxies when the universe was only a few hundred million years old and providing new constraints on how the first supermassive black holes grew to the masses required to power the most luminous quasars seen in the early universe. There is no indication that we have found the largest galactic structure the universe has produced. There is no theoretical ceiling that has been reached. The records that stand today will be exceeded. The frameworks we use to understand them will be refined and extended. And somewhere in the 85% of the northern sky that Loafer has not yet surveyed, somewhere in the southern hemisphere that the square kilometer array will map with unprecedented sensitivity, somewhere in the deep radio universe still hidden by the limited capabilities of current instruments, there are structures waiting to be discovered. Structures whose existence is predicted by physics, whose scales we can estimate based on the properties of the environments that produce them, but whose specific forms and positions remain unknown. The opportunity to study the largest galaxies, to measure their properties, to test theoretical models against observations, to probe the fundamental physics of black holes and jets and cosmic web magnetization using the extreme examples that nature has provided, exists now in this epoch of cosmic history and will not exist indefinitely. That is one more reason why the discoveries made by Loafer and the observations that will be made by the Square Kilometer Array matter so deeply. They are capturing a record of the universe in a particular phase of its evolution, when the structures built by gravity have reached their most impressive extent before the slow dissolution of the far future sets in. The largest galaxy we have ever found is both a physical object and a chapter in a longer story. It is the current answer to a question that science has been asking for as long as human beings have looked up at the sky and wondered how large the universe is and what it contains. The question will keep generating new answers. The instruments will keep improving. The universe will keep showing us more of itself. If you want to follow that process as it unfolds, as new records are broken and new structures are discovered, the best thing you can do is stay curious. Keep asking questions and remain part of the conversation. Liking and subscribing means you will be here for the next answer when it arrives from across a billion light years of cosmic space. The sky holds more than we have seen. It always has. The universe at every scale we probe is stranger, more complex, and more vast than our previous best understanding allowed for. And the story of what the largest galaxy is will keep being written, one observation at a time, by researchers building instruments powerful enough to see what no one has seen before and asking questions clear enough to recognize the answer when it finally arrives. The history of astronomy is, in many ways, the history of discovering that things are larger, older, and more numerous than previously thought. When Galileo turned his telescope on the Milky Way in 1610, he resolved it into individual stars for the first time, revealing that the faint band of light across the night sky was not a cosmic mist, but a vast accumulation of stellar points too numerous and too faint to distinguish individually with the naked eye. That discovery pushed the known scale of the cosmos far beyond anything previously imagined. The universe was not the tidy sphere of nested celestial spheres that ancient astronomers had conceived. It was something far stranger and far larger. 3 centuries later, Edwin Hubble's observations of Cepheid variable stars in the Andromeda Nebula established beyond doubt that the faint smudges astronomers had catalogued as spiral and elliptical nebulae were in fact entire galaxies, each comparable to the Milky Way in size and stellar content, scattered across distances so great that even light required millions of years to cross them. The universe was not the Milky Way plus a modest surrounding neighborhood. It was a cosmos containing billions of galaxies, each itself containing billions of stars, organized into structures spanning hundreds of millions of light. The scale jumped by another factor of millions. And now, with instruments like LOFA and surveys of the deep radio sky, we are discovering that even the galaxies themselves can produce physical structures through their jets and their lobes and their interactions with the surrounding medium that extend across tens of millions of light-years. Each generation of instruments has pushed the scale of the known universe outward, and there is no reason to expect the current generation to be the last. Every time a fundamentally new type of observation became possible, whether it was Galileo's telescope, Hubble's systematic photographic survey, the first radio telescopes, the launch of space-based X-ray and ultraviolet observatories, or the modern networks of synchronized radio antennas that constitute instruments like LOFA, the result was the discovery of phenomena that were invisible to previous instruments and that required significant revisions to our understanding of the cosmos. The phenomena were always there. They were simply waiting for the right tool to make them visible. This history should make us appropriately humble about the current limits of our knowledge. The universe, as we currently understand it, with its 2 trillion galaxies, its cosmic web of filaments and voids, its supermassive black holes and giant radio lobes, is the universe as revealed by instruments available in the early 21st century. Future instruments will reveal phenomena that are currently invisible to us, just as Galileo's telescope revealed phenomena invisible to the naked eye. And LOFA has revealed phenomena invisible to the optical telescopes that preceded it. What those future revelations will be is, by definition, unknown. But the history of the field strongly suggests that they will include structures larger and more complex than anything currently recognized. Physical processes operating at scales and intensities currently beyond our observational reach, and phenomena that will require revisions to current theoretical frameworks. Consider the observational tools that have made current discoveries possible, because they represent some of the most ambitious engineering projects in the history of astronomy. LOFA is not a conventional radio telescope. It is a distributed network of thousands of simple antennas spread across Europe, coordinated by a central supercomputer that processes the signals from all the antennas simultaneously and combines them to produce the equivalent of a single radio telescope with a collecting area that spans an entire continent. This technique, called aperture synthesis or interferometry, allows LOFA to achieve resolutions and sensitivities that would be impossible for any single dish antenna of comparable cost. The fact that LOFA has been operating for less than 15 years and has already revolutionized our understanding of giant radio galaxies gives some indication of how rapidly the field is advancing. The square kilometer array will extend this approach to an entirely new scale, with receiver stations distributed across southern Africa and Western Australia. It will combine signals from thousands of antennas spread across 2 continents, achieving sensitivities and resolutions that exceed any existing radio telescope by a dramatic margin. Its survey speed, the rate at which it can map a given area of sky to a given sensitivity, will be orders of magnitude faster than any current instrument. The scientific return will be transformative across many areas of astronomy, from the search for biosignatures in the atmospheres of exoplanets to the detection of gravitational waves through their effects on the timing of pulsars. But for the study of giant radio galaxies and the largest galactic structures, it promises to reveal a population of objects that current surveys can only hint at. When the square kilometer array begins its all-sky surveys, expected in the late 2020s and early 2030s. Astronomers anticipate discovering giant radio galaxies in numbers that dwarf current catalogs. The statistical properties of this population, its size distribution, its redshift distribution, its relationship to the properties of the cosmic web, will provide constraints on the physical mechanisms that govern jet growth and on the contribution of giant jets to the thermal and magnetic history of the intergalactic medium. These constraints will, in turn, feed back into models of galaxy formation and evolution, improving our understanding of the processes that shape the universe we observe. Understanding the extreme cases also informs our understanding of the ordinary, the processes that produced IC 1101, hierarchical structure formation through gravitational collapse and mergers, feedback between supermassive black holes and their host galaxies, the connection between galaxy growth and cosmic web structure, are all versions of processes that also shaped the Milky Way. Our galaxy has a smaller central black hole, a more modest merger history, and a less extreme environment than IC 1101, but it is a member of the same physical category of objects, subject to the same physical laws, shaped by the same types of processes operating at different intensities. Understanding the extremes is therefore not separate from understanding the ordinary. It is part of the same enterprise, approached from the direction where the signal is strongest and the phenomena are most clearly observable. The largest galaxy we have ever found is whatever the most sensitive instrument currently operating has most recently revealed. It is a moving target, and the direction it moves is always toward greater scale, greater complexity, and greater physical consequence. The observable universe, with its 93 billion light-years of extent and its 2 trillion galaxies and its vast networks of filaments and voids and the structures that inhabit them, may represent only a small fraction of the total cosmic volume. The full extent of cosmic structure, including whatever lies beyond our horizon, is unknown and may be unknowable in principle. That is one of the genuinely humbling realizations that the study of extreme galaxies delivers. Not that the universe is large in a way that can be measured and catalogued and filed away, but that the largest things we have found exist within a sample whose total size we cannot determine, within a universe whose full extent we cannot reach, producing phenomena whose ultimate range we cannot yet calculate. The largest galaxy we have ever found is the largest galaxy we have found so far. The distinction matters, and the universe, as it has done at every previous moment in the history of astronomy, is almost certainly preparing to show us something larger still. There is also a deeper question that the study of the largest galaxies raises, one that connects galactic physics to fundamental questions about the nature of the universe itself. The observable universe is bounded by our cosmological horizon. Beyond that horizon, we cannot directly observe anything, but there is no physical reason to believe that the universe ends at our observational boundary. If the universe extends beyond the observable horizon, and most theoretical frameworks suggest it does, potentially far beyond, then the structures we observe within our horizon are a sample of a much larger cosmic population. The largest structures we have detected, the giant radio galaxies, the massive galaxy clusters, the cosmic web filaments spanning hundreds of millions of light, are not necessarily the largest structures that exist. They are the largest structures accessible to our current instruments within the observable universe. The full extent of cosmic structure, including whatever lies beyond our horizon, is unknown and may be unknowable in principle. This is a genuinely humbling realization. The 93 billion light-years of observable universe, with its 2 trillion galaxies, its countless giant radio structures, its cosmic web of filaments and voids, may represent only a small fraction of the total cosmic volume. The largest galaxy, we have ever found tells us something profound about what the universe can build. But it does not tell us what the universe has built in its full, inaccessible extent. And that gap between what is measurable and what exists is one of the most intellectually honest positions science can occupy. We know a great deal. We know that seedy galaxies form through billions of years of galactic cannibalism at the centers of galaxy clusters. We know that supermassive black holes can generate relativistic jets that thread through the cosmic web across distances of tens of millions of light years. We know that the structures around us are transient features of a universe in a particular phase of its evolution, one that will not persist indefinitely. What we do not know remains vast. We do not know whether there are galactic structures beyond the range of any instrument we will ever build. We do not know the true maximum size that a radio jet can reach in the most favorable cosmic environments. We do not know how many IC-1,000-1-100-100-100 scale galaxies exist beyond our observational horizon, embedded in clusters we will never see. We do not fully understand why the universe produces the range of galactic structures it does. From dwarf galaxies containing a few million stars to seedy giants containing 100 trillion. From radio sources spanning a few 100,000 light-years to lobes extending 26 million light-years and counting. These are open questions, and they will drive astronomical research for decades to come. The study of the largest galaxies is, in the end, the study of the universe's capacity to build. Gravity, given enough time and enough matter and the right initial conditions, can assemble structures of extraordinary scale and complexity. The 100 trillion star monuments at the centers of massive galaxy clusters, the relativistic plasma clouds threading through the cosmic web, the dark matter halos encompassing all of it in invisible, gravitational envelopes that define the architecture of the observable universe. All of this assembled from the nearly featureless conditions of the early universe. One gravitational interaction at a time, over 13.8 billion years. The largest galaxy we have ever found is both an answer and a question. An answer to what gravity and time can build. A question about what else, in the vastness of what we cannot yet see, has already been built without our knowledge.